Okay, so at the end of last class I mentioned that this might be an interesting calculation to explore. We saw that this, the form minus y dx plus x dy over x squared plus y squared, well that's a closed form, and consequently this integral is path independent on a star-shaped region, right? So, for example, the slit complex plane has 1 as its star center, and a possible star center, of course, and so we can define the argument of z like such. All right. Now, so here's an example of how that looks. So if I want to calculate the argument of 1 plus I, which of course we know is pi over 4, right? Because it's pi over 4 degrees standard angle. Then I have to parameterize the line from 1 to 1 plus I. And so I put x equal to 1, I put y equals to t. Right, 1 plus it, or it plus 1 if you like, for 0 less than t less than 1, parameterizes that line. So we got dx is 0, dy is dt. Sorry, I keep finding a way to put an I in. There's no I there. Y is the imaginary component, so it itself is real. Okay, so then that gives us integral of dt over 1 plus t squared, but of course we know that's an elementary integral. That's inverse tangent. Inverse tangent of 1 minus inverse tangent of 0. Well, inverse tangent of 1 is pi over 4. Inverse tangent of 0 is 0, so lo and behold, pi over 4. So it's kind of funny. Although we seem to be coming back to the inverse tangent again, right? Which is kind of how we got here, if you remember what I did in class. Another example. Suppose I want to find the angle, the argument of minus 1 plus I. So that's over here. So I know that's going to be like pi over 2 plus another pi over 4. So it should be at 3 pi over 4. That's what we expect for the argument. And so what I did was I did this L path. I did first the green path and then the brown path. So we already parameterized the green path in example 1. The brown path, if you want a line segment that goes from 1 plus I to minus 1 minus I, you can use this this formula right here, a standard trick from Calc 3. Essentially, the point plus t times so the initial point plus t times the final point minus the initial point. That gives you the parameterization that you want. The i's cancel, and it just gives you a minus 2t there. So I get x equals 1 minus 2t. Of course, y is equal to 1 along the path. So we get dx is minus 2 dt, dy is equal to 0. And when you plug that in over here, right, work out the calculus here, and we get integral from 0 to 1 of 2 dt over 1 minus 2t squared plus 1, which, after a u substitution, is the integral from 1 to minus 1 of that, which again is getting me back to an inverse tangent. This time, inverse tangent of minus 1 minus inverse tangent of 1, which gives me a net of minus pi over 4 minus pi over 4, but then that minus and this minus cancel and give me pi over 4 plus pi over 2, which gives me the desired 3 pi over 4. So it's kind of cool. I mean, whatever. Yeah, just, I don't know. While I was at it, I figured I'd do a couple more, just for kicks. You know, am I suggesting this is how we should calculate arguments? Absolutely not. Am I suggesting that understanding these calculations is useful to you? Oh, yes, I think so. Because you're definitely going to need to know how to parameterize, parts of circles and parts of lines, and everything I'm writing down here. It gives examples of those. Anyway, so find the argument of I. So I need to parameterize this. I decided to use a unit, part of the unit circle to get to I from 1. And so e to the it parameterizes the unit circle. Of course, that's cosine plus I sine, which gives me x is cosine, sine is y. Here's your dx, here's your dy, and of course this whole thing simplifies down to dt, which I think is essentially a calculation we did in class. And then when you integrate from 0 to pi over 2, you get pi over 2, which of course is the argument of I. Alright, so, whatever. I thought, okay, well I'm going to do something a little bit more sort of greedy. I said I'm going to calculate the standard angle of an arbitrary point on the positive real axis. So to go to C, where C is, I'm assuming C is bigger than 1 here, I guess, but definitely not less, well, I said c is greater than 0. So, all right. I'm in the middle of something, Dan. Mom just went to pick up your siblings from the piano teacher. So here, integrating from 1 to c, I can use this 1 plus t times c minus 1. As you can check, t equal to 0 gives us 1. T equals to 1 gives us 1 plus c minus 1, which is c. And of course, y is equal to 0 along the whole path. So dx is this, dy is that. And the funny thing that happens is when you calculate this, the integral of the form, plug in these things right here into there, right? That's essentially the definition. Then you get 0 over something which is non-zero, which is just 0. Right, so of course we kind of knew that already. The argument of any point on the positive real axis is 0. Now, on the other hand, I thought it might be useful to finally end this little calculation video here with an example which doesn't work. So I said, well, what happens if you try to just integrate from 1 to the negative real axis? How does this break? And the reason it breaks is because that line goes through 0, and when you go through 0, you have x squared plus y squared being 0, which makes this integral not even be defined, right? So, but it would be interesting perhaps to continue this discussion and try to look at other paths which cross the forbidden zone and see how that messes up the angle that you calculate. You should be able to get values for the integral outside minus pi to pi by violating the prescription of not crossing the slit in the slit complex plane. But anyway, that's it for now. And again, not encouraging you to calculate arguments like this, but perhaps some of these calculations are useful. Thanks.